High-pressure synthesis protocols for LAH10, YH6, and YH9 below are step-by-step recipes, adapted from reported high-pressure syntheses for the three leading rare earth superhydride superconductors. All procedures use a diamond anvil cell, DAC, loaded with hydrogen, H2, or an H2 donor and employ pulsed/continuous laser heating to drive metal-hydrogen reactions at megabar pressures. 1. LAH10 materials. Elemental lanthanum foil, 99.9% purity, thickness approximately 10 to 20 micrometers. Hydrogen gas, ultra-high purity, or ammonia borane, NH3BH3, as solid H2 source diamond anvils with 40 to 100 micrometers culettes. Gasket rhenium or tungsten, pre-indented to approximately 30 micrometers with a 40 to 60 micrometers hole. Procedure gasket and sample loading pre-indent gasket to approximately 30 micrometers thickness. Drill a 40 to 60 micrometer sample chamber. Place La foil fragment in chamber. Surround with NH3BH3 powder if using solid source. Gas loading if using H2 gas. Seal DAC in a gas loading system at 200 to 300 bar H2. Cool to approximately 77 Kelvin to condense H2 and trap it in the chamber. Formation indicated by cubic PM3M diffraction peaks of approximately 2.93 angstroms. Characterization: resistive drop near 224 Kelvin at 160 gigapascals confirms superconductivity. Raman: attenuation of H2 vibron and emergence of lattice modes around 400 to 800 centimeters to the -1 power. 3. Y. H9 materials, yttrium powder or foil, H2 gas, or N, H3, B, H3, standard DAC, setup procedure. Sample preparation load Y plus H, 2 source in approximately 40 micrometers chamber. Compression raised to 180 to 200 gigapascals. Thermal activation. Laser heat hotspot to approximately 1,500 to 2,000 Kelvin for short, 1 to 10 seconds, bursts. Reaction shifts stoichiometry toward YH9, hexagonal P63/MMC, by approximately 3.60 angstroms, C approximately 5.67 angstroms. Diagnostics. XRD, splits in 100/002 peaks consistent with YH9. 4 probe transport. TC approximately 243 Kelvin at 200 gigapascals. Key practical tips: pressure ramps, slow, incremental loading, 1 gigapascal per minute, minimizes diamond failure. Laser spot size, 10 to 20 micrometers to confine heating to metal. Avoid direct H2 dissociation in chamber. Heating repeats. Multiple pulses often improve phase purity. Pressure calibration. Use both ruby and diamond Raman for cross-validation above 100 gigapascals. Hydrogen source choice. NH3, BH3 avoids specialized gas loading rigs, but introduces boron residues. Verify phases by XRD. Beyond the cell scale-up routes. Consider large volume presses, multi-anvil, at 100 to 200 gigapascals, combined with resistive or inductive heating for gram-scale superhydrides. Isotopic variants. Repeat with D2 or ND3, BD3 to probe isotope effects on TC. Mixed rare earths. Co-compress mixtures of La/Y/Ce for ternary superhydrides with tunable structural motifs. With these protocols, you can target LAH10, YH6, and YH9 superconductors at record high TC, unlocking pathways to room temperature superconductivity under pressure. Compression. Gradually raise pressure to 150 to 170 gigapascals. Monitor via ruby fluorescence or Raman shift of diamond edge. Laser heating. Focus an IR laser approximately 1064 nanometers onto La sample. Ramp temperature to 1000 to 1500 Kelvin for 5 to 30 second pulses. Observe sudden darkening or X-ray diffraction signature of LAH10 formation. Verification. Cool to ambient temperature at pressure. Collect synchrotron X-ray diffraction. Expect FM3, MLAH10 phase, a approximately 5.1 angstroms. Resistivity measurement, 0 resistance onset, approximately 250 Kelvin, near 170 gigapascals. 2. YH6 materials, yttrium foil, 99.9%, 10 to 20 micrometers thick. H2 gas or solid, NH3B, H3DAC with approximately 50 micrometers Culets. Regasket procedure assembly. Prepare gasket and chamber as for LAH10. Load Y foil and H2 source. Gas loading /NH3BH3. Decomposition gas load H2 at 200 bar, or rely on in situ NH3BH3 arrow H2 plus residual BNH during heating. Pressurization increase P to 160 to 180 gigapascals. Laser heating steps. Heat to 1200 to 1800 Kelvin in pulses, 5 to 15 seconds, to fully react Y plus H, 2 to YH6.